Okay guys, this one today is going to be to do with energy, or what goes up must come down. So, three ideas that I want to cover today. I am writing this on the opposite side. Work, potential, kinetic. Alright, takes energy to do work. Work is in fact defined as energy. So work is Fs. So some sort of force over some sort of distance. If you apply a force over a distance, it takes energy. The size of that force and the size of that distance determines how much energy exactly. So if you're applying a force of, say, 10 newtons over 5 meters, 10 meters now, it takes 100 joules of energy. Okay, so if we've got some object, 10 newtons, so about a kilogram water bottle, and you're picking it up in one room and moving it 10 meters into another room, it's just taking you 100 joules of energy to do that. Okay, so that's what work is. Work is related to these two guys over here. Alright, so potential energy. If you get your 10 newton, your 1 kilogram object, and it's down here, and you lift it through a height. So you're applying a force to move at a distance. So what we're going to do is lift this up, whatever it is. Let's say 2 meters. So here's our 1 kilogram object, and we're going to lift it up 2 meters. Okay, so the amount of work that it's taken, the amount of energy that it's taken, W equals Fs. Alright, so it's taken some sort of force over some sort of distance. In this case here, what we're doing is battling gravity. So Newton's second law, F equals ma. We're going to use G for gravity. And this specific version of S, the distance, we're actually going to say is the height that we've moved it through. So the work, or the energy, work is energy, is mgh, mass times gravity times height. So it takes us, in this case here, mass 1 times 9.8, that's gravity, times by 2 is 2 lots of 9.8 at 19.6 joules worth of energy. Alright, so we've got this 1 kilo mass water bottle, and we've lifted it 2 meters in the air. That's taken 19.6 joules of energy. Okay, so we've actually lifted something, we've given it potential energy, gravitational potential energy. Now, once it's got that energy, it's kind of stored in there. It wants to get it back, I guess. It's got it now, so it's got this 19.6 joules worth of energy, and what it wants to do when you let it go, there's no more force holding it up there. It's not on the shelf anymore, whatever it is, it's in free fall. Now it's free to experience this gravitational acceleration, and what it will do is gain that energy back in the form of kinetic energy. Kinetic energy is the energy of movement. The faster things move, the more kinetic energy they have. A heavy thing moving at the same speed as a light thing has more kinetic energy than the light thing does. So we can say that the energy, the half mv squared, this is kinetic energy. So kinetic energy, Ke, is the half mv squared. This energy here is this energy here, is this energy here, is this energy here. Okay? So we can actually look at this and go, oh, that's mgh. Alright, so you can look at these two things and say, righto, well, all it's going to do when we lift it up is we're converting energy, giving it potential energy, converting physical, chemical energy, I guess, in your muscles, whatever, lifting it up. We're putting this into the system. When we let go, we're getting this back from it. So on its way down, it's converted, so let's say it's 1 meter off the ground here, it's converted 1 times 9.8 times 1, so 1 meter instead of that, equals 9.8 joules of energy into kinetic energy on its way back down. And obviously on its way back down, it's speeding up. Okay, so when it's moving, when we lift it up, we give it potential energy. When we let it go, it converts that potential energy into kinetic energy. So it can convert all of it back. So once it's down here, we've got 1 times 9.8 times 2, which is our 19.6 joules again. But once it's back down on the ground, it's actually got that as kinetic energy. So this would be our half mv squared is 19.6. At this point here, half mv squared is 9.8. It's just that this one and this one here, these two speeds, different. It's going faster here because there's more energy, slower here because there's less energy. Alright, it's still got half of this energy, it's only halfway down. Half of this energy is still gravitational potential energy. We haven't converted all of it just yet. Alright, so using this, you can actually look at the height you lift an object, and ignoring wind drag, all that sort of crap, you can actually work out how fast it's going to be going by the time it hits the ground. So I'm going to go find another colour. Hopefully the white one wants to work for me today, and look at mgh is a half mv squared. Alright, I want to get this on its own, so I'm going to put a box around it. Remember, is it on the top line? Yes. If it wasn't, we would shift it so it was. It's on the top line, we leave it there. Alright, so v squared stays here. Now we have to move everything else away from it. Alright, so remember, first question, is it on the top line? Yes, leave it there. If it's not on the top line, we move it so it is. Then we write it down, we write an equal sign down, so it, the equal sign, everything opposite it. mgh is opposite it at the moment. Now we go back and we say, right, this half and this m have to go. This 2's down the bottom line. This m is on the top line, so it goes down the bottom, and we're left with v squared equals 2 mgh over m. Hopefully you sputtered it already. That m cancel out. So we're left with v squared equals 2gh, or v is the square root of 2gh. At no point does it matter how heavy this thing is. Once you've let it go, ignoring wind drag and all those other things, the speed it finally reaches is 2 lots of gravity times the height that you dropped it from. Alright, that means that a car off the top of a building, or a brick off the top of a building, or a tennis ball off the top of a building will end up hitting the ground at the same speed if we ignore wind resistance. Okay?